How do Routh-Hurwitz and Nyquist analyze control system stability? Imagine you're trying to keep a spinning top balanced on your finger. If it wobbles too much or falls over, it's unstable. Engineers face a similar challenge when designing control systems. They need to know if a system will stay steady or become chaotic. Two main tools help with this: the Routh-Hurwitz criterion and the Nyquist plot. Both methods look at how systems behave but in very different ways. Let's explore how each one works and why they are so useful. The Routh-Hurwitz criterion looks at the characteristic equation of a control system. This equation is a polynomial that contains all the information about the system's poles, which are points that tell us about stability. If all these poles have negative real parts, the system is stable. But calculating these roots directly can be tricky, especially for higher-order systems. So instead, the Routh-Hurwitz method builds a table from the coefficients of the polynomial. By checking the signs in the first column of this table, engineers can quickly tell if any roots have positive real parts. If there are no sign changes, all roots are in the left half of the complex plane, meaning the system is stable. If there are sign changes, it indicates the presence of unstable poles. This method is fast and effective for testing how changing parameters, like gain, affect stability. It's especially popular in electrical engineering because it helps tune feedback systems without solving complex equations. On the other hand, the Nyquist plot takes a different approach. It looks at how the system responds to different frequencies. The open-loop transfer function, which is how the system behaves without feedback, is evaluated at various frequencies along the imaginary axis. These values are plotted on a complex plane, creating a Nyquist plot. The key is to see how many times and in which direction this plot encircles the critical point -1 plus 0 in the complex plane. Each encirclement relates directly to the number of unstable poles in the closed-loop system. If the plot encircles the point in a certain way, it indicates the system might become unstable when feedback is applied. This graphical method makes it easier to understand how gain and phase shifts influence stability. It's especially useful when you have frequency response data or want to analyze robustness and gain margins. Both methods are widely used in electrical engineering but serve different purposes. The Routh-Hurwitz criterion is quick and algebraic, perfect for initial stability checks and parameter tuning. The Nyquist plot offers a visual and intuitive way to see how the system responds across frequencies, helping engineers understand stability margins and robustness. Engineers often start with the Routh-Hurwitz method to ensure the system is stable, and then use the Nyquist plot to fine-tune the design and check how much gain or delay the system can handle before becoming unstable. In summary, the Routh-Hurwitz method checks the polynomial coefficients to find unstable roots without solving them directly, making it a straightforward stability test. The Nyquist plot, meanwhile, uses frequency response to visualize how the system behaves and how close it is to instability. Both tools are essential in electrical control system design, helping engineers build systems that stay steady and reliable under various conditions.